It looks like every time we do a calculation involving a new mass and its corresponding displacement, we're computing a slightly different value for k. Does that mean that the spring constant is actually changing a little bit every time that we hang a weight on the spring? Well, probably not. It looks like there's a process at work that's causing our measurements to be slightly off every time we make one. A good first step whenever we're trying to figure out what's up with our data is to plot it, to look at it visually, and to see if we can spot what's going on.
In order to figure out what's going on, we're going to have to look at the data. And here's a couple Python procedures to help us do that. The first procedure here, getData, its job is to read the data in from a text file where we've entered the data. So it opens the file, and the first line of the file is just a header line that describes the format of the data in the rest of the file. We don't need that here, so we'll read in that line and discard it. And then for all the other lines in the data file, we'll read each of them in. They come in as each line comes in as a string, and then we're going to take that string and split it into substrings that correspond to the non-blank portions of the line. So the first substring is the first non-blank portion of the line, which will be the data measurement, and the second substring is the second non-blank portion of the line, which is the mass measurement. We then go off and convert those two strings into floating point numbers and append them to the appropriate list that we're using to accumulate the results. And when we're all done, we return the masses and the distances in two separate lists. The plot data routine is now takes over, and its job is to plot the data. So it goes off and first reads in the data. And the reason that we've separated the reading in of the data, the I/O, from the analysis, or in this case the plotting, is in case the format of the file changes, of the data file changes in the future, we'll only need to rewrite the getData portion of the Python procedures. The first thing we do once we get the data is to go off and convert it into the PyLab array data type, a very handy data type for doing numerical manipulation. And here we see an example of how handy it is. On the next line, we want to multiply each element of the xvals array by the gravitational constant. In other words, what we're doing is we're busy converting the masses that we measured into the forces that they applied to the spring. And this statement here, an array times a constant will multiply each element of the array times whatever that constant is. The rest of the procedure goes off and then creates a plot, plotting the forces applied against the distances measured. The data points will appear as little blue circles, so the B means please make it blue, and the O is please make them a circle. Let's run it and see what the data looks like. Here's the results. We can see we get the sort of plot that we might expect. The x-axis is the force that was applied to the spring. The y-axis is the displacement we measured. And here are all the data points that we measured from applying everything from the 10th kilogram up to the full kilogram weight. Let's see what we can make of that. So is this what we were expecting? Well, our hypothesis tells us that this should be the relationship between the weight and the extension that we measured. That implies that if we sort of solve this for the extension, that we expect it to be the mg, which is, so this guy here is the force, divided by the spring constant k. So that means that what we expect, so all the measured points to fall on a line with slope 1 over k. Graphically, what that would mean is that we'd expect to find some line where that had all the data points on it, and the slope of this line should be the inverse of the spring constant. At least that's what this equation here is telling us. Well, that's not quite what we got. Let's see if we can figure out what went wrong. So what did we expect was going to happen? Well, we have this theory. So we have this notion that there's a linear relationship between the force that we apply, so here's a particular force, F sub I, and the observed extension. So we have this prediction, so this will be our prediction for the ith force, and our prediction for what the offset should be is equal to the force divided by the spring constant. So this is a line of slope 1 over k. Well, what actually happened is we have some measurement up here, and that measurement differs from the prediction by a certain amount. So here's my ith observation. And there was clearly some sort of error that crept in. And so if we have this sort of model that what really happened was here, but because of some error in our process, we actually made a slightly different observation, maybe we'll make some progress if we think of it that way. So here's the error, and that's the difference between the ith observation and the ith prediction. So the question is, what can we know, what can we say about what our expectation is for those errors that are creeping into our measurements? In many experiments in the real world, the errors that we're seeing are actually the accumulation of many small random effects. For instance, a position measurement, such as the one we're taking, might be affected by the sums of all sorts of little vibrations, the footsteps in the room, machinery across the room, machinery down the hall, that's causing the small vibration which causes our error measurement to be off somewhat. Let's sort of see how that might affect our experiment. So what I want to do is to model errors so we're going to model the errors that we're going to measure basically as random numbers. So this is the assumption that the errors aren't really related directly to the experiment we're making. They're effects that are added on to the results of the experiment. And just sort of see what's going on, I'm going to show you a probability density function here for a particular class of errors, which are distributed between. So this will be the errors basically will lie in the range between +1 and -1. So this is basically between -1 and 1. And the idea is that with this particular probability density function, that the errors are much more likely to be small than they are to be large and close to 1. So let's run a little experiment, and here's our experiment. First thing we're going to do is to draw 100 numbers from that probability distribution. So we can write some Python code that says, using this probability density function, please give me a random number between -1 and 1, and we'll choose 100 such numbers. Then we're going to sum them up. So each one of those numbers that we draw will represent a small error from some random source, and it's really the cumulative effect of all those errors that we'll want to do. So we're going to sum them, and obviously sort of the smallest value we should get should be like -100, and at the other extreme we might get something as big as +100 as the sum. We're actually going to see what the distribution looks like. Having done that particular sum, we'll save it away in a histogram and repeat 10,000 times. So we're going to build a histogram of what all the sums look like, and we're going to do it for 10,000 such experiments. Let's write a little program and see what the results look like. Here's a Python procedure, test errors, that will let us run our little experiment. What test errors does is for the number of trials that we've asked for, in this case the default value for trials is 10,000, it will go off and select a certain number of points, in this case 100, from a particular probability distribution, in this case a triangular distribution that goes between -1 and 1. So that's exactly the distribution that we graphed on the slide. It will then sum up the results of each of those random selections, and then it will keep a list of all the sums that it creates for all 10,000 trials that we're doing. When we're done, we're going to plot the results in a histogram using the handy hist function from Pylab, and let's see what we get when we do it. So I'm going to save this out and run it. Of course, with 10,000 trials of 100 points each, it can take a little time to run. And here we see the results. What we have is that what this little graph is telling me, that of the 10,000 trials, some 650 of them resulted in a sum which was exactly 0. That's a little surprising, but maybe not too surprising. We had pretty much an equal chance of having a negative error and a positive error, and we expect many of the errors to end up canceling each other out. And that's sort of what we see in this diagram. The highest probability of the sums are grouped right around 0, and then that probability drops off dramatically as we get into situations where many errors would have had to have been on one side of the distribution, which becomes increasingly unlikely as the number of trials grows. So What we're going to do now is to think a little bit about what we see here. So what we saw from our little experiment looking at the effect of the accumulation of many small errors is that the net effect of all the errors being added together has a probability distribution that looks like so. And that's a curve that we've seen many times. So that, the result is that the probability of all of our sum of the errors, that probability distribution converges on the normal distribution as the number of trials in our experiment increases. So if we, instead of doing 10,000 trials, we had done 100,000 or 1,000,000 trials, we would start to see that the histogram would trace out very precisely a normal distribution. Sort of amazing. Another observation that comes to us courtesy of the central limit theorem. And that basically tells us that we get the same result no matter what error distribution that we choose. We chose that triangular distribution, but we could have chosen a uniform distribution or a Gaussian distribution, or in fact any distribution that has a finite mean and variance. So the only requirement is that we get the distribution have a finite mean and variance, and if so, we'll get the same convergence to a normal distribution if we look at the accumulated sum of many small errors. And in fact, they don't even have to be identically distributed. So what's sort of amazing is that if our errors that we're seeing in our experiment are the result of the accumulation of many small random processes, we can actually say something about the probability distribution of those errors. Let's just quickly remind ourselves what the normal distribution looks like. Here it is over here plotted for a bunch of different values of the variance sigma squared. The distribution is completely characterized by two parameters. One of the parameters is the mean, and that's the central axis of the distribution. In this case, we are plotting functions with normal distributions with a mean of 0. The other measurement is the variance, which is a measure of the width of this curve. With those two factors in hand, we can actually write a little equation that describes the PDF, the probability density function, for a normal distribution. So that's f of x, and we have a normalization constant, which is 1 over the square root of 2 pi sigma squared. And then we get the exponential part. So it's e, and it's minus x minus the mean squared, all over sigma squared. You can see what that means. That is, the argument x gets bigger, the probability associated with that becomes exponentially smaller. There's some special names we apply. If mu is equal to 0 and the variance is equal to 1, we call that the unit normal, or maybe the standard normal distribution. So let's put all of it together. So when our observation errors are due to the accumulation of many small random processes, so perturbing the measurements ever so slightly, we can say something about the likelihood that the error will be of a certain size. And we just use our information about the errors being normally distributed to write the following formula. So this is really just the information from the previous page, except here I've made the assumption that the mean is 0, which implies that the errors balance out over time. And that's typically true of many error processes. Now this is actually a really neat fact. It basically tells us that large errors, are basically much less likely, exponentially less likely, than small errors. And we're going to use that fact now to go back and finish the analysis of the data points. But it was really important to get establish how the measurements we're taking are differing from our expected predictions. And now we're going to use this information about this probability distribution, this likelihood distribution, to help us figure out the best way to sort out the actual data, the actual predictions from the observations that we made.